Hello, I'm Nami Ogawa, a PhD student at the University of Tokyo. Virtual reality researchers have developed a number of interaction techniques where users' physical hand movements are remapped onto different virtual hand movements. For example, haptic retargeting and redirect touching create the discrepancy between the position of the real and virtual hands to effectively provide passive haptics. Such techniques are called as hand-remapping techniques. A common challenge in the hand-remapping techniques is that when the offset between virtual and real hands increases, users become aware of the remapping. According to prior research, the detection threshold for the horizontal and vertical linear remapping are estimated to be only up to 4.5 degrees in any directions, which are quite narrow ranges. The purpose of a study was to investigate if representations of the virtual hands affect the detection thresholds for the hand remapping to address this challenge. Now I'm going to explain why we focused on virtual hand appearances. In the first place, why does hand remapping work despite hand displacement? The hand remapping techniques are typically explained by visual dominance over proprioception. However, it can be also said that these are a type of body ownership illusions where a virtual hand is felt as one's own hand and the virtual and real hands move correspondingly. Now let me briefly explain the mechanisms of body ownership illusions. The sense of body ownership emerges from a combination of top-down and bottom-up processes. The top-down factors refer to appearances of a virtual body. Previous studies have shown that the closer the appearance of the virtual body is to our own bodies, the stronger the sense of body ownership. On the other hand, the bottom-up factors refer to synchronous multisensory or sensory-motor stimuli. So the displacement between the real and virtual hands weakens the body ownership illusions because vision and proprioception become incongruent. The point is that regardless of the amount of hand displacement, the strength of the body ownership can still be manipulated by the avatar appearances in top-down processing. However, hand remapping techniques have rarely been associated with the body ownership illusions. Ownership was the first study to mention the importance of the body ownership illusion in a hand remapping technique. The authors considered the sense of body ownership to be a requirement in the technique they proposed and evaluated the sense of body ownership. In contrast, our idea was to find a factor that accounts for the sensitivity to the hand remapping based on the evidence from the body ownership illusions so that we can improve the hand remapping techniques regardless of the remapping algorithms. These backgrounds have motivated us to investigate how avatar appearances influence the sense of body ownership and the detection threshold in the hand remapping techniques. Realistic virtual hands have shown to increase the sense of body ownership, but it's still unknown how much they affect when hands are remapped, so we investigated. In addition, we hypothesized that realistic virtual hands can also make the remapping less noticeable by fostering the sense of body ownership over the remapped hands because both are a matter of self-attribution. Compared to the effect on the body ownership, this hypothesis is not necessarily obvious because the detection thresholds are related to the self-attribution of a movement or the sense of agency. So we conducted an experiment. The experiment mainly consisted of two tasks, namely a remapping detection task and a self-localization task. The main task was the remapping detection task, which measured how sensitive participants were to the remapping. On the other hand, the self-localization task was conducted to measure the proprioceptive drift, which is the displacement of proprioceptive self-localization toward a virtual hand from the actual hand position. This is an established objective measurement of the strength of the body ownership illusions. Regarding the remapping model, we use the horizontal linear remapping because it's a common and basic form of the hand remapping. The experiment was conducted with 16 right-handed participants, and all the tasks followed as within subject's design. We used Oculus Rift CV1 as a head-mounted display and lip motion controller to track the participants' hand movements. Let's look at the mapping detection task first. In each trial, the participants reached for a virtual button with their right virtual hand, which is horizontally remapped. Then they judged if the movement of the virtual hand exactly matched the movement of their own hand in two alternative force choice tasks. The shift amount, which was defined as the distance between real and virtual hands when the virtual hand reached the button, was varied between trials according to a staircase procedure. For example, when the participants answered no to the question, which meant that he or she was aware that the movement was remapped, the staircase algorithm reduced the shift amount for the next trial. By repeating that, the staircase method can efficiently find the detection threshold. In half trials, the virtual hand was replaced by a virtual sphere. It's an abstract avatar. In addition, the detection thresholds were estimated for each shift direction. Finally, the staircase algorithm needed 28 trials to converge for each condition. Here's the actual setup. The participant reached for the button and answers whether the movements of real and virtual hands exactly matched. Now let's move on to the self-localization task. The participant first reached for a virtual button as with the mapping detection task. But when the button was pushed, the virtual hand and the button disappeared. Then the participants estimated the position of their actual index fingertip. Let's say the perceived proprioceptive position is here. The participants answered this position by shifting the virtual board using a control held in their left hand. During the estimation, they had to hold the position of the real hand. The proprioceptive drift is defined as the distance of the actual position to the estimated position. Each participant conducted 40 trials. They consisted of 2 avatar appearances and 5 shift levels from -10 to +10 centimeters. Please remember that the shift direction is from real to virtual, so the positive values indicate the rightward shift. And lastly, a trial for each unique condition was repeated 4 times. Here's the actual setup. She reached for the button and answered her actual index finger position by shifting the board position. The conditions for the 2 tasks can be summarized like this. In addition, we conducted a heartbeat counting test to assess interoceptive sensitivity, which has been shown to predict the susceptibility to the body ownership illusions. So we expected that interoceptive sensitivity may also account for one's sensitivity to the remapping. Furthermore, the subjective sense of embodiment was assessed through a questionnaire. However, I'll leave out the details regarding these tests today, so please read our paper for details. Let's take a look at the results. If you look at the detection threshold for each condition, you can see the significant difference between realistic and abstract avatars for leftward shifts. In fact, we found a statistical difference between these numbers as a result of a two-way ANOVA and Turkey's post-hoc tests. In addition, when we calculated how much the realistic avatar increased the detection threshold compared with the abstract avatar for each participant, we found the threshold with the realistic avatars to be 31% higher on average for leftward shifts and all the participants had a positive ratio, which meant that the effect of avatar appearances was applicable to anyone for leftward shift. As for the proprioceptive drift, we observed a very similar trend. As I explained earlier, the proprioceptive drift is defined as a bias from real to virtual hand positions. What we were interested in was the effect of avatar appearances, that is, the differences between orange and green plots. So please take a look at these asterisks. With abstract avatars, the proprioceptive drift hardly occurred. In contrast, with realistic avatars, the proprioception was drifted to the virtual hand position. To summarize, these results show that compared with an abstract avatar, the realistic avatar makes the remapping less noticeable and brings the proprioceptive hand position closer to that of the virtual hand in case of leftward shift. In other words, realistic avatars can foster the self-attribution of movements as well as the self-attribution of a body. In addition, even though the proprioceptive drift is considered to be a measurement of the strength of the body ownership illusions, it indicates that when realistic avatars are used, visual information is given greater importance in visuo-proprioceptive integration as compared to abstract avatars. So why is the avatar appearances effective only in the case of the leftward shift? To answer this question, we may first consider what was different between left and rightward shifts in essence. In fact, they were not symmetric against body midline in terms of real hand movements because the participants used the right hand. When you try to reach out your right hand for each direction, you will notice that how muscle was used was totally different, and you might feel a change in the sensitivity to the proprioception. In addition, when leftward shift is applied, the hand moves in the direction away from the body midline. The distance from body midline has been said to influence the body ownership illusion because it is related to the paired personal space, which fosters multisensory integration. Probably because of these differences, our results in fact showed anisotropy regardless of avatar appearances. The detection thresholds and the proprioceptive drift were both lower for leftward shifts than for rightward shifts on average. So we consider that the realistic avatar fosters the self-attribution of a body and movements when the visuo-proprioceptive integration hardly occurs. Future work includes to further strengthen the sense of body ownership by means other than avatar appearances, such as adding synchronous visual-tactile stimuli like passive haptics to further increase the detection thresholds. Another interesting prospect is to dig deeper into the effect of avatar appearances. For example, it is known that a stronger sense of body ownership can be elicited with a virtual limb that appears to be connected with one's torso than a virtual hand without an arm. In addition, it remains unclear if the avatar appearances linearly affect the detection thresholds. So it will be interesting to know how the detection threshold will be when the avatar is of medium level of realism, such as robotic virtual hands. Lastly, our recent study indicates when users use controllers for input, displaying the controllers instead of realistic virtual hands increase the sense of body ownership, even though they are objects. So the effect of showing the realistic virtual hands might depend on the input modality, and further investigation would be needed. To conclude, we showed that the use of realistic avatars instead of abstract avatars can improve the hand-remapping techniques by making the remapping less noticeable without changing the mapping model itself. In addition, we show that the perception of the hand remapping may be related to body ownership illusions. I'll conclude my presentation with a take-home message. Be sure to use realistic avatars when you want to enable larger displacement while ensuring that the mapping is less noticeable.